Today's lesson is from Chapter 5, Section 5.1. And what we're going to be looking at are discrete probability distributions. And our objective is to construct a probability distribution for a random variable. So let's back up for just a moment and talk about what a random variable is. Now, if you recall, a random variable is a variable whose values are determined by chance. Remember when we talked about variables and the way these values are determined. And there's two different categories for a random variable. They are discrete or continuous. Now, with a discrete random variable, the main thing you want to keep in mind is those are always countable, whereas a continuous random variable is something that's always measurable. So what we're going to be focusing on in section 5.1 are discrete random variable, things that are countable. Moving on. So a discrete probability distribution consists of the values of a random variable can assume and the corresponding probabilities of the values. So we're looking at the values of the random variable and their probabilities. Another fact is the sum of the probabilities of all events in a sample space must add up to 1. So, and each individual probability must be something between 0 and 1 inclusively. Okay, so we're pulling together what we know about discrete and distributions with a random variable and probability that we had in chapter 4. So let's look at a problem. So for our first example, I have here that the experiment is to flip a coin, and in flipping this coin, flip a fair coin 3 times. What is the sample space? Now remember how we determined this. To flip this coin 3 times to get the sample space, you have to consider all the possibilities. So there's things like heads, 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 tails. Well, to make sure you don't leave anything out, it's probably best to create a tree diagram. So in this tree diagram here, we have following along the branches, we can now list our sample space. So our sample space here is going to be heads, 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 reading across the top branch. The next one is heads, heads, tails. The next one is heads, tails, heads. The next one is heads, tails, tails. Another outcome is tails, heads, heads. Then tails, heads, tails. And then tails, tails, head. And then the last outcome is tails, tails, tails. So in flipping this coin 3 times, we have 8 outcomes in our sample space. Now, if I let x be the random variable for the number of heads, now what that's saying is that I'm saying how many heads are possible in these outcomes that I had when I flipped a coin 3 times. Well, let's go back to that. So like in the very first outcome over here, we've got 3 heads. And then this outcome, there are 2 heads. And then we can go down, in this outcome, we have 1 head. And then in this outcome, there's 0 heads. So the number of heads that are possible could be either 0, 1, 2, or 3. So that's going to be our values of the random variable. Now this probability distribution looks a lot like a frequency distribution, except our frequency distributions were usually listed as columns. A probability distribution is usually listed horizontally in rows. So this right here, this first row, those are the values of the random variable. X could be either 0, 1, 2, or 3, meaning the number of heads. Then we want to get the probability of those occurring. So the way we do that is we go back and look at our sample space to get 0 heads. How many times did that occur? Well, let's see, 0 heads. Go back to the problem here. 0 heads was this outcome right here. This was 0 heads, where we have tails, 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 and there was only one like that. So the probability of 0 heads is 1/8. Now to get 2 heads, one head, the outcomes could be this, that's 1 head, this outcome has 1 head, this outcome has 1 head. So that's it. You've got 3 outcomes that consist of 1 head. So when I go back and look at my probability distribution, that's what's occurring here, is this 3/8 is 3 out of 8 outcomes for 1 head. Then for 2 heads, going back to my probability distribution, for the 2 heads, let's see if I can get a thing here. Okay, so I'm looking at this outcome has 2 heads, this outcome has 2 heads, this outcome has 2 heads. So here again, I've got 3 outcomes out of 8 that have 2 heads. And then I only have 1 outcome up here that has 3 heads. So looking back at my distribution for 2 heads, I have 3 outcomes out of 8. For 3 heads, there was 1 outcome out of 8. So my probability distribution looks like this horizontal 2 lines, X being the top one, and the second row is going to be the probability that that occurs. Now, if I want to construct a probability distribution for rolling a single die, what I have to think about is, what are my outcomes? Well, when I roll a single die, what are those outcomes? They are just, my sample space is just the numbers 1, 2, 3, 4, 5, and 6. Those are my possible outcomes. So when I could create this distribution, those are going to be the values of X. And then I need to think about, what's the probability that I roll a 1? What's the probability I roll a 2? So my probability distribution looks like this. So to roll a 1, that occurs 1/6 of the time. To roll a 2 is 1 out of 6. Probability of rolling a 3 is 1 out of 6, and so on. So that's my probability distribution for rolling a single die. Now, going back to tossing the 3 coins and the number of heads, the one we looked at earlier, sometimes we're asked to represent this graphically. And all that means is you're going to create a histogram for this distribution. Well, on the histogram, my lines are not very straight. I know yours are much better than this, but we want to mark off the horizontal axis with the values of X. So that's going to be the 1, 2, and 3. That's the number of heads. And then our y-axis are going to be the probabilities of that occurring. So that's the probability for those number of heads. And notice here our probabilities go from 1/8 up to 3/8. So I would probably just mark it off like that. 1/8, 2/8, kind of equally space this out. 3/8, like that. And then when I get ready to sketch this, I'm going to place a bar above the 0 that's centered on the 0 that goes up to 1/8. Good gracious. Something like this. And then a bar above the 1 that goes up to 3/8. And then one above the 2 that's centered above the 2 that goes up to 3/8. And then 3 is 1/8. So my histogram looks, well, yours is going to look a lot better than that. But anyway, so that's what the graphical representation of that probability distribution is. So it's very much like what we did with frequency distributions. The only difference is This y-axis is the probability that X occurs. Now, not all probability is classical or theoretical. Sometimes we have empirical probability we work with. Remember, that's where some data was actually gathered. So in this example, we have the World Series is played by the National League and the American League winners. So in baseball, there are two leagues that play each other all season long. The National League teams play each other and the American League teams play each other. Well, at the end of the season, there is a winner of the National League and a winner of the American League. So they play against each other, those two teams, for the World Series. And that usually occurs in October. And the situation is this, that the first team to win 4 games wins the World Series. Well, it could be a situation where a team comes up and wins all 4 games right off the bat. They're a very strong team. So they win game 1, win game 2, win game 3, win game 4, it's over. And what we have found out that's happened in the past is down here in our frequency distribution that occurred 8 times. That winning the series in 4 games happened 8 times over the last 40 years. Now, sometimes it took 5 games. That occurred 7 times for the series to be won with 5 games. So that would mean that one of the teams would win 3 games, the other team would win 1. They still don't have a team that's won 4, so they have to play a 5th game to get a winner. And they keep doing that, and so it's possible they may have to play 6 games. Each team wins 3 and 3. Or they may have to play 7 games. In that case, one team would win 3, the other team would win 4, so that team would be the winner of the World Series. Well, if I wanted to construct and graph a probability distribution of that, what it would look like, let me see if I can add a slide in here. Oops, sorry. Okay, so I've gathered my thoughts, and for this part, I'd like to construct a probability distribution and graph it. So I have a blank screen for us to work with. And so the number for X, the number of World Series games could be 4, 5, 6, or 7. So in our distribution, this is our probability distribution. We have X and then the probability of X. So X was 4, 5, 6, and 7. And then to get the probabilities, we go back and put the frequencies divided by the total number of frequencies. So we got 8, 7, 9, and 16. Let's see if I can get that in here. 8, 7, 9, and 16. And this was out of 40. So I haven't reduced the fractions here. I'm just writing them all down as relative frequencies, which is the same thing as the probability. So that's our probability distribution, this right here, that X, the value of X and the probability that X occurs. And then we're asked to represent this graphically. So along the X-axis, we're going to have our 4, 5, 6, and 7. And then the y-axis has got to go as high as 16/40. So we might want to mark this off, I don't know, maybe in 5s, 5/40. So this would be 5/40. And you could reduce these fractions, 10/40, 15/40. And then, oops, 20/40. And this is the probability of X occurring. And this is X. And then we just center our bars above the values of X. So on the 4, we're going to center a bar. I'm going to estimate about 8/40. Center a bar on the 4. And then estimate about 7/40. So it's a little bit less on the 5. And then 9/40, that's a little bit more. So not quite 10. And then